I'm Rachel Boislar.
I'm Anna Kirchie.
And I'm Steve Tricarico, and we've completed our senior design project for the Department of Chemical and Biomolecular Engineering at UConn. Our project was to design epoxy potting of caps for capillary filtration.
Capillary filtration is just one step in an industrial water filtration process. It occurs after large particles are removed from the water, but before water is sanitized, and it primarily removes undesirable particles such as iron and magnesium. The filter consists of two materials: thin, hollow silica glass fibers encased in an epoxy that holds the fibers together. The feed stream of water passes through one end of the filter, and clean water is filtered out through small pores in the capillary fibers. The process is not 100% effective, so filtration usually consists of multiple passes through the capillary filter, or multiple capillary filters lined up in a sequence.
To manufacture a capillary water filter, liquid epoxy has to be poured onto the delicate glass fibers and allowed to harden, a chemical process known as curing. Epoxies are a type of polymer created when a resin and a hardener are combined and allowed to cure. They are thermosetting polymers, meaning once they are hardened, they cannot be reheated and reused with the same functionality. Everyday epoxies include adhesives, paints, coatings, and sealers. The issue is that the curing reaction is very exothermic, and the heat that builds up within the epoxy is transferred to the glass fibers, causing them to break due to an accumulation of thermal stress.
The initial goal of this project was to develop an understanding of the kinetics of the epoxy curing reaction and to model this reaction in COMSOL with respect to the geometry of a capillary water filter. To appropriately evaluate the model, we had to create a temperature profile of the reactor as a function of the curing time. Our end goal was to design a strategy to prevent the glass capillary fibers from breaking under thermal stress while limiting changes made to the functionality of the water filter.
The most accurate model for studying epoxy curing reactions is Kamal's model. This differential equation allowed us to determine the degree of curing, alpha, as a function of time. The reaction constants were calculated using the activation energy and frequency factor, which are known epoxy parameters. The total heat associated with curing is also a known parameter. And with the knowledge of the degree of curing from Kamal's model, we were also able to calculate the heat released at any given time throughout the reaction. Kamal's model was discovered through patterns in empirical data gathered by differential scanning calorimetry.
DSC is a technique used to determine physical properties pertaining to the enthalpy of materials, such as the heat capacity and flux. It also allows for the determination of how the extent of curing changes over time. This example DSC data from a paper on Kamal's model shows the heat flux, and therefore rate of curing, increasing greatly during the middle of the process. It then tapers off towards the end as the cure concludes. We see that the plotted points from the DSC instrumentation deviate only slightly from the solid curve derived from Kamal's model.
Using COMSOL, we were able to build our desired geometry and define the materials associated with each domain. We applied Kamal's model to the epoxy and generated temperature profile graphs to examine the heat flow from the epoxy to the remainder of the reactor. A real capillary water filter would consist of several bundles of these hexagonal shapes, as you can see on the right, but for modeling purposes, we focused on one hexagon.
We ultimately decided to vary 3 parameters to determine the best possible solution for the problem. The first is varying the initial temperature of the reactor, the second is selecting the material of the capillary fibers, and lastly, we varied the porosity of the epoxy by introducing an inert filler. All of these are compared against our initial controls of 380 Kelvin, glass fibers, and negligible porosity in the epoxy.
Another parameter we decided to vary is the material used for the capillary fibers. To determine the best possible material for these fibers, we ran the model with various epoxies. Here, we will discuss which materials worked best and why.
The next parameter we altered was the initial temperature of the reactor, which also determines the length of time it takes for the epoxy to cure. We ran the model with initial temperatures ranging from 320 Kelvin to 400 Kelvin at various intervals with a maximum time length of 80 hours. Here, we're going to discuss the ideal initial temperature and its graphs.
The final parameter we studied is the porosity of the epoxy. It is ordinarily difficult to vary the porosity of mediums like epoxy, but we can introduce an inert filler to not only impact the system's porosity, but also discover a way to help disperse the heat of reaction. We began this study in COMSOL by varying the porosity of the epoxy in 10% increments, down to 50% where the structural stability of the epoxy may be compromised.
Here we will discuss the chosen optimized parameters based on the previous 3 slides.
Further research for this project would include physically testing our solution and creating a real model of the improved capillary filtration system. If the proposed process improvements work, the overall cost to generate these filters would be lower with far reduced risk of unsuccessful manufacturing. This project is important because developing ways to improve this water filtration strategy can potentially expand access to these filtration systems, ultimately making safe water more accessible.
We would finally like to thank our faculty advisor, Dr. Nye, for all his help in completing this project.